Welcome back to another episode of Science Unboxed with Professor Matt W. Today, we're going to look at some of the different problems that were raised with our theories on quantum mechanics. We're going to see how philosophy, quantum physics, and a brewery in Belgium are all related. All this and more on today's episode. And we're going to first start with where we left off last time, back to talking about ontology and epistemology. So ontology is, of course, the philosophy of being. That is, the philosophy of what things are. So Aristotle, for example, was a great ontologist. So was Socrates, asking questions like, what is justice? What is this animal in front of me? Is it a frog? Is it an elephant? Is this a river? It's what things are and being. Versus epistemology, which is the study of knowledge and how we acquire knowledge and whether or not knowledge fails or it doesn't. And central to the idea of the Greeks was also epistemology, the study of knowledge. Things were knowable. And in today's podcast, we're going to see if quantum physics somewhat negates the ability of, like I was suggesting last time, of the knowable universe, of what's known in the universe. But first, let me make a quote from Richard Feynman. He says, "I think it is safe to say that no one understands quantum mechanics. Do not keep saying to yourself, if you can possibly avoid it, but how can it be like that? Because you will go down that drain, you will go down that rabbit hole, into a blind alley from which nobody has yet escaped. Nobody knows how it can be like that." Well, we're going to try to attempt to see how it could be like that, or at least a universe in which the world could work as quantum mechanics suggests. So we're first going to look at a couple different things that we went over in last time's lecture, including the work of John Bell and also ontological randomness and epistemological randomness. So what does it really mean that a wave encodes probability? I keep saying that. Well, let's first recap what we learned from Bell's theorem. We said that when we go to measure what a quantum mechanical particle does, quantum mechanics let us predict the probabilities that certain answers will come up. But one of the questions people had was whether those probabilities are inherent to the physical system, i.e. the physical system that we're testing, or whether those probabilities are a statement about our lack of knowledge. That is, it's an epistemological problem. For example, one of the ideas that people had early on was that, well, maybe we can't predict what the outcome of any particular measurement will be, but perhaps that's only because there are certain hidden variables. We went over local hidden variable theory and how John Bell disproved local hidden variable theories by his famous experiment. These variables would be hidden in the sense that we do not have experimental access to them. And if this is the case, quantum systems might actually be deterministic rather than merely probabilistic. We just can't see it. And Einstein wouldn't have a problem with it. Einstein was a realist and believed in determinism in some capacity. It wouldn't violate that. Well, John Bell did his famous experiment where he disproved non-local variable theory. That means that the particle, you and the particle, let's say, are playing a card game, and the particle would have a card, and only the particle could see what was on the reverse of that card. Let's say, like I said before, it was a queen of diamonds. Well, if it's a queen of diamonds, only the particle can see that it's a queen of diamonds. We, the observer, can never see that information. Okay, but the information does exist, bottom line. In contrast to non-local hidden variables, those are variables that are outside of the scope. That means that they are not near the particle. So it's not a variable that is anywhere near the particle. It's not the particle doesn't have access to that information, or it's on another side of the universe or in another universe entirely. So we're going to look into that as well. So John Bell disproves the hidden local variable theory. And if there is a script, it is nowhere near the particle. I know this sounds weird, but this was a lot of progress for quantum mechanics. It ruled out a whole way of looking at quantum mechanics. That is, no longer did we think that the particle had any information encoded on it, almost like a barcode. And this makes sense, as we now know that every electron in the universe is exactly the same. That is something easy to say, and you intrinsically say, oh, well, that makes sense that every electron is the same. But does it really? Let's say I have a bunch of basketballs all made by the same manufacturer. Is every single one of those basketballs exactly the same, down to the most microscopic nanometer? And the answer to that is no, they aren't. Electrons are. Electrons are exactly the same. So it doesn't matter if electron is here, as in on Earth, or if the electron is on the other side of the universe, let's say 1 billion years ago, or 1 billion years in the future. Both electrons are exactly the same. So the measurement process still largely remains in a black box to us, right? So we've been able to say that it is definitely not a local variable. And it's in a black box in the sense that we don't understand exactly how it works. And in the absence of complete understanding, lots of speculations have arisen about exactly what quantum mechanics means. For example, we've seen that the state of a quantum mechanical particle can be described by a wave, and we've talked about how this wave function encodes probabilities. For example, it can tell us the likelihood of finding a particle in a particular spot, like I was talking about with the couch and the plant, or here or there. And when we go to look for it, we can measure its position. That same wave function can also tell us the probability of finding a particular answer when we go to measure other properties, like energy or momentum. So energy is important, obviously, for photons and subatomic particles, and momentum, angular position of the electron around the nucleus of an atom. So are those probabilities inherent to the physical system, a concept we call ontological randomness? And again, now we're going to talk about, is it ontological randomness or is it epistemological randomness? Does nature really operate with little rolls of the dice? That means that when I roll a dice with 6 sides, because I know there's a lot of Dungeons and Dragons players out there with 20-sided die and so on and so forth, but let's say I have a 6-sided dice. Are those probabilities merely proxies for our lack of knowledge, or are they actual things? Are they ontological things? Do they have being? Meaning that 1/6 is this thing, that a wave can be a probability. That probability isn't a thing. It isn't a random thing. It's not there for lack of knowledge, but it actually exists. If probabilities are inherent to the physical system such that when we take a measurement, the wave itself changes into a new wave in a completely random way, that is ontological randomness. So the wave itself changes into a new wave in a completely random wave. So we can never know exactly how the wave is, or we can't exactly know the position. It's always updating, pretty much. The random process is actually truly written into the fabric of nature, and it's a true description of how things actually operate. So ontological randomness, again, is saying that probability is an inherent concept, whereas epistemological randomness, well, that's going to be talking about, in lieu of our understanding, we assign probability. So we don't know where the particle is going to be. So we give it a percentage chance of being, 30% chance of being here, and or 70% chance of being there. The question becomes, is quantum mechanics ontologically random, or is it epistemologically random, i.e., it's in lieu of our misunderstanding or not being able to understand? So just to be clear, the probabilities were encoded in the wave. They are epistemological. We're using them as a calculation tool only because we don't know everything about what's happening. So we don't know everything about the system, all right? It might help to compare this to something that was discovered before quantum mechanics, and when we started talking about statistical mechanics. And it sounds like a big word, but it's applying statistics just to science. And some of the things that we take for granted, like pressure, temperature, volume, especially temperature and pressure, we use statistics to really calculate the probabilities of collisions of particles. So when we look at the temperature when we look at the temperature outside and we say it's 80 degrees today, that is a statistical measurement of a bunch of particles, a bunch of molecules hitting each other. And the faster they hit each other, the more kinetic energy you have, the higher the temperature. That's what I mean by applying statistics to science. And you might say, well, that's exactly what quantum mechanics is doing. How is that any different? Well, it isn't. because we actually could trace how each molecule moves and get a result and get a temperature. We can actually trace those molecules. We don't do that because there's an Avogadro's number amount, and that's 6.02 times 10 to the 23rd. But anyway, there's a lot of molecules. There are a lot of molecules, and we use statistics pragmatically in that situation to discuss how they move. So that's a little bit different than using statistics as saying, well, the position of a electron is 70%, let's say it's 70% 4 feet away from you and 30% 7 feet away from you. It's different because we cannot take the electron and find the answer. We can't actually trace how it behaved like we can with the molecules with statistics. Now, statistical mechanics involves assigning a lot of probabilities to exactly how, say, the molecules in your glass of water are moving about, and certain assumptions about the likelihood that each particle is doing a particular thing. And then we use probabilities to calculate the large-scale behavior. And this works exceedingly well. Again, though, it is intrinsically different from quantum mechanics. It is an application. And you could say that, like I said in the previous lecture, you could say statistical applications to science form genetics. Before we knew about DNA and genes, we knew about genetic traits and how traits were inherited. Blonde hair and blue eyes would be if two people were to cross. If we knew their family members, their grandparents and their parents, we could have a pretty clear understanding of what the genetic traits of an individual would be. So that's an application of statistics in a similar capacity to the applications of statistics to thermodynamics. All right. So we could track how each molecule of water moves, but we use statistics, again, for practical purposes, as I suggested. And this is an example of epistemological randomness, where we use statistics for our lack of knowledge. And it works quite well, but it doesn't work perfectly. So probabilities also take on a prominent role in quantum mechanics, but it's being employed in a very different way, like I said. And some people would debate this with me. Some people would say it is actually being used in the same way. But I think most people would say it isn't, because we can trace the molecules, like I said, into a deterministic behavior that creates the temperature or the pressure of a system. This underpins something that there are huge arguments between physicists. And the physicists would be so heated in debate that the mantra became, shut up and calculate. Don't worry about the philosophical implications or knowing how things work. And this gets to a much deeper rooted idea in the scientific method. I don't think everyone knows exactly how the scientific method works, because we're taught the scientific method in elementary school and in middle school and high school and college, etc. But I'll never forget when I got to graduate school and learning about the null hypothesis and the idea that the common idea is that we have an idea. So if it's how science works, the common conception is I have an idea, okay, that's based in some type of predictive mathematics or some type of predictive ability. So I have an idea, and I want to go out and I test it. I either do an experiment or I take observation. Certain sciences, for example, like quantum mechanics and chemistry and hard sciences, you can do an experiment, you can get a result. Other sciences, let's say astronomy, we can't control how stars and planets work, right? So we have to collect observational data. And you can go into other sciences, the softer sciences, for example, anthropological and sociological sciences, like, for example, archaeology, which I participated in. And you could say an event has already happened, okay, and I'm collecting evidence, but how does the collection of that evidence really support whether or not that event happened? Because I can never reproduce that experiment. The reproducibility factor of science is not able to be constructed in some of these sciences. You can only observe. The real point is that the scientific method is a little bit different than what you were taught in school. And the main ideas of the scientific method are first that you have an observation or question like we talked about that you want to test. You form a hypothesis, right? And the hypotheses are formulated as testable statements subject to falsifiability. Falsifiability becomes the most important part of the modern scientific method. And you create two hypotheses. You have the null hypothesis and you have the alternative hypothesis. And what you're trying to do is gather enough information to reject the null hypothesis in favor of the alternative hypothesis. So let me give you an example. So there is a very popular brewery in Belgium that creates a beer with a pink elephant on it called Delirium. And it's a very popular brewery in Belgium, probably the most popular, and it's in Brussels. And if you go there on any particular night, there's tons of people there. And I'm sure there are some people there that would claim that they see the pink elephant. They've imbibed too much alcohol and they can see pink elephant. So how scientifically would that person, that drunk, how would they prove that there is a pink elephant in the room? Well, first, the hypothesis, of course, that they would first, of course, say that they've observed the pink elephant, and they would develop some questions, and they would have to develop two hypotheses. The first hypothesis would be that the null hypothesis, which is that there is no pink elephant in the room, which is probably the correct hypothesis. The second hypothesis is that there is indeed a pink elephant in the room. So the drunken scientist would take observations. They would maybe use tools, videographic, and find evidence of this pink elephant. And the evidence comes back, and they analyze it, and it's enough information so that they can't throw out the null hypothesis that there is no pink elephant in the room. And so they have to accept that the null hypothesis is possible, and they can't throw it out. Now, if I really wanted to be a real scientist, and let's say it's something that does exist in the room, let's say, just for our purposes, let's redo the experiment, okay? And we have a scientist that is sober in the Delirium Brewery, and for some reason, there was a quantum leap, and there was a pink elephant in the bar, right? So the same thing happens, okay? The scientist now is, of course, sober. He finds evidence of the pink elephant through some type of video or some type of quantum experiments. And he develops enough information where he can throw out the null hypothesis that there is no pink elephant in the room in favor of the alternative hypothesis, which was what his initial idea was, which is that there is a pink elephant in the room. Okay. And this all centers around the idea of falsifiability, being able to falsify one's hypothesis. And of course, statistics is involved. You have p-values, and you can have different p-values and intervals depending on how exact you want to be. Other portions of the modern scientific process also then develop theory, and you have peer reviews, and eventually you can have a paradigm shift, such as the quantum paradigm shift or the paradigm shift that was caused by relativity. So, but the main idea is that if I want to go about proving something, I don't do that. I have to disprove the opposite of what I am trying to prove. That is how science works. That is how the current scientific method works. I go about trying to disprove the null hypothesis, which is the opposite of what I am trying to prove. That's the whole point of what I'm trying to get across. That might be a little bit different than what you think the scientific process is. So what is inherent to the scientific process? And an inherent part of that is, of course, statistical analysis. Now, a sociologist that studies phenomenology, or other types, anthropologists that use autobiographies and other type of data, could disagree with me, but they would still use statistical analysis in some capacity. Overall, though, intrinsic to the modern scientific process, besides falsifiability and the idea of trying to disprove the opposite of your hypothesis, is also statistics. What does statistics mean to the modern scientific method? Well, the modern scientific method doesn't take an ontological view of randomness in the scientific process. It assumes the epistemological randomness view of statistical analysis, the thermodynamics view, the view that statistics is used in lieu of information we do not know yet. So what does that mean? Well, it means that, of course, that using the modern scientific process to assess quantum mechanics could be inherently flawed. And it's a serious problem, right? If we're using the epistemological idea of randomness when quantum mechanics is based on ontological randomness, we aren't going to get the right answer, right? We don't want to get to the right answer by accident. This is science, after all. And the reason why science uses statistics in the epistemological sense, in that we're using statistics in lieu of what we don't know. So the dice roll is just in place of an event that will occur and we will know, and to an event that we are and reproduce. It's very important to draw those distinctions, okay? So what does this really lead to? Well, it leads to a couple different ideas in the interpretation of quantum mechanics. I just want to summarize where we are so far. We've gone over ontological randomness. That's the idea that statistics themselves are things unto themselves. They aren't pieces of information in lieu of not knowing something. They exist unto themselves. Using probability in quantum mechanics is how quantum mechanics works. It works through probability, okay? Whether or not the wave is updating or whether it's not, it doesn't really matter in that capacity. Then there is the epistemological view of randomness, which is used in the scientific method, that randomness and statistics is used in lieu of understanding. Now, let's apply this to what we know about quantum mechanics. The main interpretation of quantum mechanics is, as I said last time, is the Copenhagen interpretation. The Copenhagen interpretation, sometimes called the standard interpretation, was developed by Niels Bohr and Werner Heisenberg, is what is typically taught or assumed in textbooks on quantum mechanics. The Copenhagen picture includes wave function collapse, the idea that at the end of a measurement process, the quantum mechanical particle is in a new quantum mechanical wave state. If it was not already in a pure state associated with that measurement type, then it will suddenly and uncontrollably snap into an eigenstate, like we talked about last time, eigenstate and eigenvalues of that measurement during the measurement process. This is what is known as a wave function collapse. In this picture, the wave function collapses in a random way. The Copenhagen interpretation has the interesting implication that not all properties of the particle are all well defined at any instant in time. The particles could be 3 feet, there's a 30% chance it could be 3 feet away from you, and a 70% chance it could be 7 feet away from you, okay? So that's what we're talking about here. On the Copenhagen view, the fundamental truth about what the particle is doing is contained only in the wave function, and there is nothing more that can be known about the particle before the measurement happens. And a huge limitation is that the wave function cannot be measured directly. One of the problems with the Copenhagen picture, of course, is that what is a measurement? And Niels Bohr even said that a measurement involves a quantum mechanical particle interacting with a measuring device that can be treated classically. In other words, the measurement device has enough particles in it that it can be described in classical physics as deterministic. Now, we went over in Schrödinger's cat how that's like very complicated and somewhat absurd when in some capacity. Because when I measure something, I'm probably using some type of photon or I'm using some type of light source in what I'm measuring, or just using a particle in some capacity. Let's say I add a photon to an electron, suddenly the electron is going to behave differently. Okay, it's going to collapse the wave function. So using classical models and classical mechanics, I can't truly know the nature of things like electrons. They're going to absorb the photon that I'm using to measure, right? And the measurement device is ill-defined by Niels Bohr in the Copenhagen interpretation. And that's why a lot of people have problems with it. When then would we draw the line between the particle that's being measured and the classical device that's doing the measuring? When we go back to look for what that line might be, we find that everything is made of quantum particles, and it's just hard to do. There's also an interesting insight by Eugene Wigner, which is somewhat discounted. A lot of philosophers love him. Eugene Wigner is that if consciousness is involved in the measurement process, and then the measurement process affects the particle, causing it to snap into a new state, then surely you can use your consciousness to directly affect the quantum mechanical particles. And maybe you even use this to create your own reality. So, meaning that my consciousness is a macroscopic measuring device, and just my consciousness affects the outcome of the measurement. Now, why isn't this exactly quite right? Well, if our consciousness directly changed the behavior of particles and allowed us to have measurements, I think that's almost like we could create our own reality. Why wouldn't everyone have billions of dollars? And why wouldn't everyone be driving, a Bugatti? I think there's intrinsic problems with that assumption that our consciousness is involved or responsible for the measurement process. Take that into consideration. So there's these different ideas about how we measure things, and a lot, like I said in the previous podcast, a lot of PhD work is done on measuring devices and measurement in general, especially in social sciences, because they take this to the nth degree. Social sciences will use phenomenology and autobiography and ethnographic studies, and they'll use this to create a scientific reasoning for their theory. And I believe that's not actually science, to be completely honest. That's why I'm very critical of the social sciences, psychology, and even anthropology, and, going into gender studies and all kinds of other things like that, because you're not really truly doing science. It's very subjective in that capacity. But what is subjectivity? If Eugene Wigner is correct, what is subjectivity? Because there really isn't such a thing as subjectivity. If my consciousness is always affecting the measurement, then objectivity doesn't exist and empiricism doesn't exist, which leads to all kinds of problems. And I think that's where we are in the current age. Postmodernists, again, pushed by the social scientists of the 90s, 50s, and 60s that were imbued with a lot of communist belief structures, that with the basic belief that history is really not a discussion of historical figures, but about the changes of power and power dynamics. I think all these types of sciences, multiculturalism, gender studies, sociologies, a lot of psychology, to say there's no objective world makes the positive empiricist completely wrong and nullifies much of science that brought us to the paradigm shift. And we started out these lectures by saying quantum mechanics is a new world, right? We said that there was a paradigm shift. But Einstein, just like Isaac Newton, they stood on the shoulders of giants, right? They stood on the shoulders of Aristotle, of Copernicus, Socrates, Plato, Archimedes, the list goes on. And we wouldn't have paradigm shifts or even the scientific method where we could have paradigm shifts without the positive empiricists. And you could argue also we wouldn't have science without the natural philosophers. Of course, that's true too. But I think to say that the world is completely subjective and there is no objective reality is rubbish. I think that leads to epistemological failure. And I am an epistemologist. I believe more towards Einstein view of being a realist and being the non-local hidden variable theories. I think that might be the correct approach. Over a series of lectures, I'll talk about why. But just for now, I do believe that there is such a thing as knowledge, and we can communicate, and that knowledge can be communicated to people. And if you take the opposite point of view, that there is no objective reality, I think you take the view of epistemological failure, the failure of knowledge itself, that knowledge can't be communicated and knowledge can't be known. And this is what we're trying to move from in quantum mechanics. Those that believe in ontological randomness inherent to quantum mechanics still would not argue, I think, that the world is subjective. Okay, they would still believe in an objective reality. And I think the postmodernists took some of these views. They got built up and got carried away with some of the views that were produced from quantum mechanics. John Bell called this the shifty split. So there's a split in how quantum mechanics treats objects. They're either treated as quantum mechanical particles, like we're talking about, or large-scale deterministic particles with macroscopic features. So like I said, there's the little world. John Bell is saying there's the little world where we're talking about 1 or 2 electrons, we're talking about 1 or 2 photons, very small, and things work differently for them. And then we're talking about measurement devices, and we're talking about the macroscopic world. They're large. They're composed, tons, literally 10 times 10 times 10 times, going 23 times, particles, 10 to the 23rd amount of particles just in Avogadro's amount, which is about something maybe the size of my hand worth of. So if I have maybe something a little bit small that I could hold in my fist of gold, that might be close to an Avogadro's number, maybe a little bit more, maybe a little bit less, but there's a lot of particles going on. Okay, so that's the shifty split that John Bell talks about. And in an attempt to set up a crisp definition on what a measurement means, Eugene Wigner, here, the person who's talking about the consciousness being the measurement device, proposed the key aspect of measurement process being consciousness of the human observer. In other words, human consciousness is needed to cause a wave function collapse. Now, let's think about that for a second. Does consciousness need to exist for a measurement to happen? In this day and age, we can so if I have a photon detector, so I have a interferometer, and we will eventually go into what an interferometer is, but it's basically a laser that's pointed at mirrors and lenses, and it can give me a situation. It can actually make a photon go in 2 different directions, but end up with only one result. So I have some interferometers, and I can set up a measuring device to automatically measure when a photon is being sent. I can set up my computer and it will send a photon, maybe 1 per second or 10 per second. And I can have a detector automatically detect that photon on the other end, okay, to see where it lands. And it could email me or it could tell me later on. I don't actively have to take that measurement. I can set up a computer to. And I think that shows that consciousness is not needed to make a measurement. Measurements happen with or without consciousness. Even if you want to get into debates about AI and so on and so forth and who created the computer, measurements happen without consciousness. To suggest, I think it is an invalid point to suggest this. So Wigner's idea never really gained traction, like I was saying, among physicists. The reason for this is that the measurement device that we use in the lab can record answers, as I said, whether or not we are present or not. We can set up an experiment, take measurements on some schedule, and have it record the answers as it gets it. No consciousness needed, right? Now, there is a modified version of the Copenhagen interpretation, which says that the measurement device itself is sufficient to cause wave function collapse. This is the view I've been presenting overall because it's the view that is typically taught in physics courses because it has stood the test of time and we have physical experiments to suggest this is true. It hasn't been invalidated. The idea worked exceedingly well for making predictions. So we're gonna take this view, at least right now, that the measurement device itself is sufficient to cause the wave function collapse. There's no consciousness needed. One of the problems with the modified Copenhagen interpretation, though, is that it seems to include effects that can propagate faster than the speed of light. And that's where we can get into some hairy problems. For example, in the wave function collapse idea, a measurement device way out in space may interact with one tiny part of a wave function and cause the whole thing to collapse instantaneously, even though they're interacting in a tiny part of space. Albert Einstein called this spooky action at a distance. And what I'm saying here is, so we're taking a measurement of where an electron is. And remember, an electron is just a particle electron is just where the wave has the highest amplitude, most portions of amplitude. But it might have the wave, remember, it goes on, in theory, infinitely. When I make that measurement of the electron of being here, suddenly the rest of the wave collapses and the electron is right here, right now. And that would suggest that that there's information. Like I said, 70% of the high amplitude is right here, and 30% is on, let's say, on the other side of the universe. Suddenly, that 30% is here, is where I'm detecting the electron, which would suggest that that information could move faster than the speed of light. And we'll get to this in later episodes that really delve into this idea exceedingly well. But the basic idea is that, yes, the wave function collapses possibly faster than the speed of light. Possibly. So the information at the other end of the universe that has to collapse to give me a measurement over here, where I am right now, did collapse faster than the speed of light. But we cannot use that to actually send information, okay? The wave function collapse gives us where the electron is, but it doesn't give us the information of where the other part of the wave function was on the other end of the universe. So that's how we get around the speed of light problem. And I think there's more in particle physics to help elucidate and understand this idea in theory. Okay, let's go into Einstein's view, a realist view. Remember, God doesn't play dice. So Einstein took this realist view. We went in the last lecture of the EPR experiment, which was to find that the Copenhagen interpretation was actually correct. I'm just going to go into that a little bit more. Rather than following the Copenhagen interpretation that particles may not have well-defined position or that they may not have well-defined momentum before a measurement happens, Einstein believed that particles really had those properties before the measurement, meaning that there are these hidden variables. He believed that there are hidden variables, okay? He also didn't like the idea of non-locality, which is the idea that something a long distance away could instantaneously affect something somewhere else. That's that other part of the wave function that's on the other side of the universe that suddenly collapses and allows me to see that there's an electron right here in front of me. For these reasons, he claimed that quantum mechanics is an incomplete theory, and there must be more going on. Einstein and his colleagues, Boris Podolsky and Nathan Rosen, proposed that what became known as the EPR, Einstein-Podolsky-Rosen paradox, to showcase the inadequacies of the standard interpretation. However, this proposal was experimentally tested, and the Copenhagen interpretation was vindicated. We're going to go more into detail about this, and the last podcast I did go into some detail about this, but he was vindicated with the caveat that there could be non-local hidden variables. That is, there could be information somewhere that's not near the particle. Einstein obviously didn't like about this is that it could violate the speed of light. But I think as we discover more about the symmetry of the universe and how we start breaking down space and time into its component parts and how the dimensions build on each other and seeing the universe not as it is now, but how it came to be, like where it was at the Big Bang, and then further on, how it went from being a point in space and time to being 3, 4, 2,000 dimensions, depending on what part of string theory you adhere to. And we're going to go into that. We're going to have a whole series of podcasts on string theory because that's incredibly interesting, but mostly heavily mathematically based because there's not much experimental evidence for it. And that's the real problem. There isn't an elegant experiment for string theory. It is a great theory in terms of mathematics that also hasn't been really disproven and also has proven almost every other theory of quantum mechanics, but they go hand in hand in some capacity. So that's where Einstein kind of stands. He doesn't think that God plays dice through the universe, okay? And he also thinks that there must be something more to it that we're not seeing, all right? So let's go into some of the common ideologies. So if anyone's seen Doctor Strange and the Multiverse of Madness or a lot of the Marvel movies, there's this many worlds interpretation of quantum physics. And this idea is that when a measurement occurs, the universe itself splits in half. It bifurcates into two parts. Whatever was possible given the probability set by the original wave function prior to the measurement. Those possibilities each happen in a distinct instance in another universe. So every time a quantum measurement is made, the universe splits. And we look into kind of the Marvel movies and also Loki, the show Loki, again, Marvel, which are great pop culture, I think it does delve into a lot of discussions and about quantum mechanics. It makes quantum mechanics more relevant to the general population, and also string theory if you go more into it. But it could violate many different things. For example, it could violate entropy, could violate the amount of particles in the universe, could violate the amount of universes that are possible, or the amount of dimensions that are possible in string theory. American physicist Hugh Everett originally proposed the many worlds interpretation as the relative state formulation of quantum mechanics. It wasn't taken seriously at the time. In fact, Everett was criticized, but a version of it was later revived and now goes by the name of the many worlds interpretation. Let's say electron, which is, it's in your room, okay, or in your car as you're driving, listening to this podcast. There's a wave going across your car, like from the driver's side to the passenger side. There's a wave, an electron. If we measured it, it would be where you are, where you're driving. But 70% of the wave of the high amplitude was where you are, and 30% was where the passenger was. But when you measured it, it actually came out to be where you are, because it worked with the statistics. According to the many worlds interpretation, when you go to measure where that particle is, the universe will bifurcate. There'll be one universe in which the particle ends up on where you are in the driver's seat, and there's another universe in the passenger seat. And like I said, there's a myriad of problems with this many world interpretation, but it has captured the public consciousness. And I think it's mostly because people want to think that there could be other outcomes to an event. I think it's wishful thinking, to be completely personal about it. But that's just my opinion. So the modified many worlds interpretation basically is a view where we consider that every particle in the universe should be included in the quantum mechanical description. Then we should write down a single wave function that is a many particle wave function that describes every particle in the universe. And that wave function is governed by the laws of quantum mechanics. Prior to this lecture, we've only been talking about a single particle, right? That one electron wave or one photon wave, right? Where there's 30% here and 70% there. Okay. The modified many worlds interpretation, it would be to say, let's take all the particles in the universe and let's create a single wave to describe the quantum mechanical nature. Okay. In this view, there's no distinction between the system being measured and the observer or measurement device, because by definition, they're both inside the universe, right? There's nothing outside the universe that could perform the measurement. Now, of course, a drawback of this way of looking at things is that a wave function to describe every particle in the universe at once would be rather complicated, just like when we were talking about in thermodynamics, calculating. So I have this cup of water, calculating the temperature of this cup of water by measuring the velocity of every single water molecule in my cup of water. It would be time consuming. Okay. Now we have computers now that could probably do that, but it would have been time consuming, right? That doesn't suggest that necessarily there's other universes, which I at least find better. And it also goes into more of kind of a thermodynamics way of looking at quantum mechanics in terms of the epistemological randomness. We're using probabilities in lieu of understanding of facts. Okay, there's also Bayesian probability. Again, going over, anyone that's taking a statistics course should know about Bayesian probability. And this is a completely different view of what quantum theory means. And recall that a basic question is this: what do the probabilities associated with the wave function really mean? Are they random in the sense that the particle actually behaves in a truly random way? Or are all those probabilities a proxy for our lack of knowledge? Again, going back to the question of ontological randomness versus epistemological randomness. The Bayesian probabilist interpretation view is that those probabilities associated with the wave function are epistemological probabilities. They take the view, of course, that it is an epistemological random event. We don't have all the knowledge. Bayesian view the probabilities as a statement of the current state of knowledge. On this view, when a measurement happens, we update the wave function that we were using to describe the particle, not because the particle changed, but because our knowledge about that particle changed. So we're following the wave, right? Let's think, let's close our eyes for a second. If you're in a car, please don't close your eyes. But for a second, let's think about this. Let's say you're following a light wave. And every time we take a measurement of where that wave is, well, we took that measurement, but now it's in a new place, right? And it's in a new place, and a new place, and a new place, and a new place, because that wave goes on forever, right? And it's propagating on infinitely. That's kind of the Bayesian probabilistic model of quantum mechanics. And that makes inherent sense. It agrees with the fundamental theory of science, or how scientific progress works now and the scientific method works now. It also agrees with thermodynamics, how we approach thermodynamics, and it agrees with our just intrinsic understanding of statistics and how it applies. This view has a strong following today among many people who are working on the foundations of quantum mechanics. So that makes sense, because why change everything, right? If we accept a world that is ontologically random, or we accept quantum physics based on ontological randomness, we have to change the scientific method. We have to change basically our view of science in general. The idea of falsifiability, the idea of the null hypothesis, which isn't to say that isn't correct, but if we were to use the philosophical principle of Occam's razor, which again isn't a scientific principle, it's a philosophical principle, that would be, of course, the easiest way out of our dilemma. But certainly, just because it's easy doesn't mean it's right, as anyone knows. And then, of course, there's two more things. There's explicitly non-local versions. There are also hidden variable formulations of quantum mechanics that were not ruled out by experiments by John Bell, right? Those are the non-local variables that Einstein somewhat clung to and other scientists still cling to. The most prominent example of this is the pilot wave theory developed by Louis de Broglie and David Bohm. It's a non-local hidden variable theory. The behavior of one particle depends on the current state of every other particle in the system. And so far, it hasn't made any different predictions from the standard quantum theory that would allow us to test it. So this is that every particle depends on every other particle, right? So that's why things get so strange, right? The strangeness of quantum mechanics and how we can only describe it in terms of probability is because we have, again, it's almost, I think, very similar to the modified many worlds interpretation model. One potential problem, though, to the theory is that the non-local effects are instantaneous. Again, they would have to go faster than the speed of light. However, it turns out that we still can't use those long-distance instantaneous effects to send messages with information content, like I said before. So in that sense, it does not violate special relativity, which says neither particles nor information can propagate faster than the speed of light. And that's an essential feature we're going to find with the non-local hidden variable theories violate the universal speed limit of c, the speed of light. And then, of course, there's also an environment. So all particles are part of their environment, and this is called environmental dephasing, in which there are non-local hidden variables allowed by John Bell's theorem that are coming from the environment. And this view reminds us that a particle is not isolated. It's always somewhere in some context, surrounded by some environment that interacts with it all the time. And then in this view, we can take a measurement. We need to remember that we're not just dealing with the quantum particle in the measurement device, we're also dealing with the whole environment surrounding it. And, that's an important part of the scientific method, having controls and making sure that our experiment is being conducted in a completely pristine environment. In this picture, the environment itself is constantly essentially measuring the particle already, and the combination of particle plus environment plus measuring device is the total system that determines what types of final states are accessible after the measurement. This view has a good following among physicists as well. And so really the question is, what do we make of all the interpretations? While each one fills in a lot of the conceptual details of quantum theory itself, it leaves a lot open. None of them can erase the basic weirdness that we see in quantum mechanic experiments, which is that a single electron interferes with itself when it's put through the double slit experiment. It behaves as a particle and a wave. What is the overall idea of this podcast? I want to just summarize. The scientific method is not exactly what you were taught in school. Falsifiability is an important component of the scientific method. Also, the null hypothesis and alternative hypothesis are important concepts in the scientific method. When I'm designing an experiment as a scientist, okay, And I have conducted scientific experiments. I was a scientist. I still am in some capacity. I conduct quantum experiments. I want to do more in the field. When I'm going about designing an experiment, when I come up with an idea, I am not trying to prove my idea. I am trying to falsify the null hypothesis, okay? Which is the opposite of my idea. So if there was definitely a pink elephant in the room, I wouldn't go about gathering information to prove there was a pink elephant in the room. I would actually try to disprove that there is no pink elephant in the room. That sounds a little bit strange. It is, but it is the modern scientific method. The modern scientific method is a little bit different, and you should probably read up on it because it led to a lot of confusion during the COVID crisis. And it has a lot of implications for how we conduct scientific research. It's also why what was done during the COVID crisis wasn't science. There were no null hypotheses. A lot of the research had no null hypothesis. There was no falsifiability. There was no peer review. There wasn't much time for theory development or experimentation. Science can't be done in a vacuum. It can't be done quickly. It takes time, especially when we're talking about big concepts like quantum physics or medicine or anything like that. So we need to understand the scientific method, firstly. Secondly, we have to understand the difference between ontological randomness and epistemological randomness and the ideas of ontology and epistemology. That is, that things are intrinsically random, that there are these things like 1/6 of a dice roll. That is a thing, and we just have to accept it. That we have to accept that a electron can be 70% here and 30% there. That is just a thing. That is being. That is the electron in its state of being. Okay? You have to either accept that, or we got to accept the more standard view that we've kind of experienced for the last several hundred years, which is we use statistics in lieu of information, and we use it to help us with the scientific method for analysis. The only caveat is that I would suggest is quantum mechanics points us that there is such a thing as ontological randomness, and that is a big problem. And that's what we're going to continue to explore through these podcasts. Follow me at Professor Matt W on Spotify, Apple, Amazon, and also anywhere you can, any type of social media, TikTok, Instagram. Stay curious and stay interested. Quantum mechanics is a fascinating and interesting concept. I hope to demystify it as much as I can. Thanks. Bye.